Hello chemistry people, and welcome to this discussion of 15.1 HL energetics, which is on energy cycles. So when we look at the study guide, we're going to be talking quite a bit about representative equations and this triangle from our different enthalpies. And we're going to be constructing some Born Haber cycles. The questions that I will be giving you on OneNote are focused around those. So constructing energy cycles, calculating enthalpy changes, and then separately we are going to be talking about size and charge of ions to lattice and hydration enthalpies. And I am going to talk about, in this context, one of the issues that we have when we look at the line between ionic and covalent. Okay, So obviously at the moment there are some issues with performing lab experiments. We will do some of these, but obviously not just at the moment. Yes, and I am going to be talking quite a bit about Databook usage in this. So what I would recommend, pause this video and go and get yourself a Databook, because we are going to be referring to the Databook throughout this presentation. So with all of the Born Haber cycles that we're looking at, there are some basic equations that you need to be able to understand what they are and how we can represent them. So hydration is the energy, so these are all thermochemical. It's where we take a gaseous ion, and what is the energy when that becomes aqueous? So this is delta H hydration. Now, when you're looking at these in general, what you need to be looking at is, what is my little thingy down there? What is my annotation on the delta H? Ionization is, better switch back to my pen because that's not going to work for highlighting. For ionization, what I'm looking at is, what is the energy when my gaseous atom, what is the energy difference when I remove an electron from that atom while it is in its gaseous state? Like I said, you've got to pay attention to what the little down the bottom of the delta H. With all of these, pay attention to what your states are, because of course state changes, as we're literally about to see in atomization, these state changes are really important. Those involve a change in energy. Atomization is the energy it takes for me to take something from a solid state and convert it to a gaseous state. So with all of these, we're interested in what is the delta H of that process. So for some of these you might be given the delta H. For ionizations, so first ionization energies for these guys are given in the Databook on one of the periodic table pages at the beginning. And the second ionization energy is also given for oxygen. So let's continue on and look at some more of these standard equations that you need to be able to recognize. Electron affinity is, if I start with an atom and I add an electron, again, those are all in the gaseous state. Lattice enthalpy is one of the big ones for this topic. Let me make sure that's super, super highlighted. So, lattice enthalpy is the energy that it takes for me to take a ionic lattice, Cl, solid. How much energy does it take for me to split that apart into gaseous sodium and gaseous chloride ions? By definition, according to the IB, this delta H lat is always greater than 0. It's always defined in terms of this endothermic process of breaking apart that lattice. Covalent bond enthalpy, sorry I forgot a word there, we discussed in SL. So this is how much energy does it take for me to break this into 2 chloride. So gas, and remember bond enthalpies are always in gas form. How much energy does it take for me to break that bond? So this is the bond enthalpy of Cl, and all bond enthalpies, regardless of whether or not they're chlorine to chlorine, all of those are going to be greater than 0, because remember, breaking covalent bonds is an endothermic process. Now, solution enthalpy. Earlier we talked about enthalpy of hydration, which is how much energy is released when I've got my gaseous ion and I add water to it. Solution enthalpy is the delta H of taking, and I'm using sodium chloride as an example of an ionic compound. It is, of course, not the only ionic compound. So solution enthalpy is the enthalpy change when I take a solid ionic substance and I dissolve it in water to form NaCl aqueous. So that is delta H sol. Okay, let's continue. Okay, so let's construct a Born-Haber cycle. So earlier we talked about Hess's law in SL, talking about the steps on a pathway and that sort of vector addition idea. That's what Born-Haber cycles are, but Born-Haber cycles take it that next step. So if we think about something like magnesium solid plus Cl2 gas reacts to form MgCl2 solid. This is like saying, so this reaction, it's like I take magnesium and I take chlorine, magic happens and I end up with magnesium chloride. Now, if you know anything about the scientific mindset, you know that waving arms magic happens isn't an explanation that's going to fly. So what we do is we construct a Born-Haber cycle. So I know that I start with magnesium solid and chlorine gas. And I know that I am going to end up with magnesium chloride solid. So, but what are my steps? So the first thing I need to do, I need to take my magnesium and my solid magnesium and turn it from being a solid to being a gas. What I then need to do, I need to remove one of my electrons from my magnesium. I then need to remove the second electron from my magnesium. Okay, I then need to split apart my chlorine molecule into the 2 chlorine atoms. Then once I've got that, I need to add, so this is times 2. So actually I'll do it in 2 steps. So I start with my magnesium 2 plus gas, and I take one of those electrons and I add it to one of my chlorine gas atoms, and I'm left with 1 chlorine gas left over. And then I add the other electron to my chlorine atom. So Mg2 plus gas plus 2Cl minus gas, and then that links back. So let's talk through this process again. Okay, so in order for us to turn solid magnesium and gaseous chlorine molecules into the ionic substance magnesium chloride, I need to turn my solid magnesium into gaseous magnesium. I then need to turn my gaseous magnesium into a magnesium 1 plus ion into a magnesium 2 plus ion. I then need to break apart the bond on in my chlorine molecule to give me 2 chlorine atoms. I then take one of my electrons and add it onto my one of my chlorines. I then take my other electron and add it onto my other chlorine to make my second chloride ion. Then my 1 magnesium ion and my 2 chloride ions form magnesium chloride. One thing I have done that I need to make sure that I fix before we go on to the next slide. Earlier, I made a point of discussing that we defined lattice enthalpy as that endothermic process. Have a look at the way my arrows are pointing. Okay, now what we're going to do on the next slide, actually no, on this slide, what we're going to do is we are going to label these different arrows with the delta H's that we talked about on those first 2 slides. So what we're trying to find out overall is what is the overall delta H for this reaction. So what do I call the chemical process how a solid becomes a gas? That is enthalpy of atomization. I've then got the energy that it takes for me to remove an electron. So that is first ionization energy. Then I've got the second electron coming off, which is second ionization energy. Then I'm splitting the bond between my 2 chlorine atoms, so that is the bond enthalpy of a chlorine to chlorine. Then if I go over to the right hand side, I've got the first electron affinity for chlorine, and then the first electron affinity for chlorine again. So this is the first and second ionization energies over on the left for magnesium. And then the electron affinity for chlorine. Now this big arrow, and I mentioned it earlier, this is my delta H lattice. So let's quickly look at the bits and pieces of information here that we already know. Lattice enthalpies, a lot of them are given in the data book. Electron affinities, first ones, are given in the data book. first ionization energies are given in the data book. So the first ionization energy for our elements is given, but not our second. So our question might be to work out what is the second ionization energy if they gave you the overall delta H, or it might be they give you this second ionization energy and they're asking you to calculate this delta H, because bond enthalpies, we use those in SL. You know that that's in the data book. So my big recommendation for doing these Born Haber cycles, give yourself as much room as possible. Don't try and squidge it down into some tiny little thing, because it's really easy to miss steps. You need to make sure that you're working really methodically. So I did all of my processes to my magnesium before I touched my chlorine. Do that. Work through super methodically. Do all of your manipulation of one of your elements before you go on to the other one. Now, the Born Haber cycles that you are going to be looking at are for group 1 or 2 metals, and then either halogens or oxygen. So like halides or oxides. So you need to make sure that you are covering all of these arrows. Okay, so what we're going to do now, I am going to copy and paste over this diagram onto my next slide and actually start filling in these numbers. I might actually go back to and grab a picture of the Born Haber cycle before I did this purple annotation. But we're going to start putting some numbers to this. Okay, so my recording might sound a little bit disjointed on this one because I am going to be pausing the recording while I find various bits and pieces in the data book or on the internet. So while I'm on the page of the periodic table, page of the data book that gives me ionization energies and electron affinities. So this is -349, -349. I would recommend in the future just doing 2 times and just having the 1 arrow. But while doing this first one, I did just want to emphasize that it was step by step by step. So we've then got our first ionization energy for magnesium, which is +738. Now, all of these values that I'm writing in are in kilojoules per mole. So let me pause while I go and find maybe some bond enthalpy data. Okay, so I flipped to section 11 for bond enthalpy data. This bond enthalpy for the chlorine to chlorine bond is +242. Okay, let's go to my next. Okay, so I will go through this again later on, but in the data book we are told that the lattice enthalpy for magnesium chloride is +2540. So we just need to find the second ionization energy. Sorry, this should be plus. Okay, so I am just after the delta H of atomization and the second ionization energy. Give me just a second. Okay, so the second ionization energy of magnesium is +1. Oh, I've forgotten which way around those numbers go. +1451 kilojoules per mole. And let me now just Google up the delta H of atomization of mag. So this is plus 148. Okay, so the only number we don't have is our delta H of reaction. So what you do is you literally, just like we followed the arrows when we looked at the diagram versions of Hess cycles, you follow this around. So, and I'm literally going to type it into my calculator as I'm going. I start with plus 148 plus 738 plus 1451 plus 242 plus, because I'm agreeing with the arrow, negative 349, and then I'm adding, because I agree with the arrow, negative 349, and then I'm subtracting, because I disagree with the arrow, 2540. So overall, that gives me a delta H of reaction of negative 659 kilojoules per mole. We will be doing more practice of these when you look at the questions I've already grabbed for you. This is something that, because there are so many small parts to it, it is something you will need to practice. But if you get stuck when doing those questions, come back to this video and then re-watch how I constructed the cycle and work through just really methodically is my main tip for this. Okay, so in general, there is a connection when we look at some properties of my ions and then some properties of the ionic lattice that they are a part of. So I'm just going to quickly draw up an ionic lattice for us. And I'm sorry if anybody's red-green colourblind, but those were the two colours I decided to pick. So when we talk about the properties of our ions, we talk about ionic radius, and we talk about the charge on the ion. There is one caveat to all of this that I will discuss at the end, but these are linked to the properties of our lattice. Because if my ionic radius is small, that's going to lead to an increase in that electrostatic attraction. Which means that we're going to have increased lattice enthalpy because there's more force, more of that electrostatic attraction holding those ions together, so it's going to take more energy for us to rip them apart. However, if my ionic radius is larger, there's going to be a decrease in that electrostatic attraction, which means that we're going to see a decreased lattice enthalpy. So the charge on the ion. So if you compare like a 1 plus ion versus a 2 plus ion, so a sodium lattice compared to a calcium lattice, that increased charge is again going to increase that electrostatic attraction, which is going to lead to an increase in lattice enthalpy. So something like calcium oxide is going to have a larger lattice enthalpy than sodium oxide, is going to have a larger lattice enthalpy than sodium chloride. Now, there is one little asterisk, and you know it's tricky when there's an asterisk on like an ad and it says down the bottom conditions and exclusions may apply. Similar sort of thing here, but there are limitations. So in SL, we talked quite clearly that there is a difference when we talk about ionic, be good if I could write, ionic versus covalent. And we were very clear about there are ionic compounds and there are covalent substances, and there's no Venn diagram there. There's no overlap. Not quite. So there is a task that we may not have time to get to, but it's actually a really lovely one. Looking at how good lattice enthalpies are at actually discussing whether stuff is ionic bonded or covalently bonded. So there are some ionic lattices that do not fit those two trends that we just talked about, ionic radius and the charge on the ion. And that's because instead of one atom giving up its electrons to the other, they kind of share them in a very polar covalent bond. So there are some outliers here, and it's because, of course, nothing is ever that simple. It was never going to be as simple as ionic versus covalent. There is always going to be some sort of Venn diagram overlap. Now, to the best of my recollection, the IB have never asked specifically name a substance that. However, they can say, I believe I've seen some questions that explain why there may be outliers in this data trend. And this is one of the possible answers to that. Okay. So let's use this table from the Databook. This is a direct screenshot from the Databook to talk about what I was describing on the previous slide. So as I go from lithium down to cesium, I'm talking about an increase in ionic radius. And what is happening to the lattice enthalpy with fluorine? Lithium fluoride, both really small ions, both so really close together, so high lattice enthalpy. All the way down to cesium fluoride. Cesium's a very large ion, which leads to a decrease in electrostatic attractions, which means that it's got a comparatively lower bond enthalpy. If you compare sodium fluoride to magnesium, let's compare sodium chloride to magnesium chloride. The magnesium ion and the sodium ion are very nearly the same size. It's not exact, but one of them is the 2+ ion versus the 1+ ion. Those lattice enthalpies are remarkably different. So if you forget those general trends, you do have the data to back it up. And this is, as I said, directly from the Databook. Let's look at some of the other information the Databook gives you. So this is the bond enthalpy table. Please also remember that there are the multiple bonds given below. I didn't have room to put it on this page and have it still be readable. One of the really easy mistakes is when people are reading and they're in a hurry and they're stressed, they won't read the chlorine to chlorine. They will accidentally, when they're stressed and they're rushing, they will suddenly just write down like 324 and then continue on with their calculations. this is where having rulers can be really helpful for you during the exams, just so you can physically like run the ruler along a line. Okay, so if I take lithium chloride solid and I dissolve it in water to form lithium chloride aqueous, the delta H sol, and that's a standard, is going to be not an arrow, duh. So the delta H sol is going to be minus 37.03. So enthalpies of hydration. Sorry, my recording on the last one got a little bit cut off, but I can't be bothered going back to put the endpoint on kilojoules per mole. So these enthalpies of hydration, so if I take a beryllium gaseous ion and I dissolve it in water, my delta H of hydration standard, I don't know why I keep putting arrows. My delta H of hydration is going to be negative 2,524 kilojoules per mole. So what does that do for us? What does lattice enthalpies and solution and hydration do for us? They do this for us. So if I've got calcium chloride solid and it's becoming calcium chloride aqueous, that is my delta H sol. Calcium chloride solid to calcium gas and chloride gas, that is my delta H lattice. Then calcium gas to calcium aqueous, that is my delta H hydration for calcium 2 plus, and this is 2 times my delta H hydration for Cl minus. So if, for example, if you're asked to find a delta H of solution for something that you don't have the delta H sol in the data book, but you do have a lattice enthalpy and a delta H of hydration, you can work it out. This is a Hess's cycle using the information that we have been accessing to create our Born-Haber cycles. So this is why I've called it the triangle of Databook. So if I've got my hydrations and my solution but not my lattice enthalpy, I can work it back that way as well. Okay, so this limitations of the model, this is what I discussed in that previous one. So before, we literally talked about, and this is probably a diagram that I literally drew for you. I wouldn't have had you guys for Year 10 Science, but it's something that I literally draw in Year 10 Science. So we're told, or you were told, that what ends up happening is my sodium ends up completely giving away its electron to chlorine, so that I end up with Na plus and Cl minus. However, when we start dealing with larger atoms, when we're looking at stuff that maybe has a lower electron affinity than something like chlorine, it doesn't so much take it as have a high degree of custody of. It's almost closer to one of the very polar bonds that we look at in intermolecular forces for H bonding. The uneven distribution of that charge is so strong to almost be ionic, but it's not quite ionic and it's not quite covalent. As I said, it is in that Venn diagram overlap. And also, electrons are so small and moving so fast that we are most of the time giving our best guesses on where they might be. So saying that they spend all of their time with one particular atom, that's a bit silly given how weird electrons are. Okay, so in this, we've talked about the representative equations. We've talked about the energy cycle for our 3 Databook values. We've constructed a Born Haber cycle, but there is more practice of that. I will put a question on hydration, lattice and solution enthalpy. We calculated enthalpy change, but again, there's more practice on the questions. We've talked about the size and charge of ions. We haven't done any lab experiments. We talked about the enthalpy terms, and I went through the places in the Databook where we can get that information. Okay, that brings us to the end of 15.1 on energy cycles. I have put a whole stack of questions into the OneNote for us to practice with. If you've got any questions, please do let us know. And I shall see you next time. Bye.